So this unit is, as you thought, it's about exponential functions, and you did study them a little bit in Algebra 1. But this unit, of course, will go much deeper than you did then. Good news, only the first section involves any kind of graphing, and it's pretty light. Okay? In fact, this unit and the next unit will all be pretty light graphing. We'll focus much more on procedures, applications, solving, that kind of thing. You will learn a new... So that's the first half of this unit. The second half is all about logarithms and inverse functions. And that's something that I don't think probably anybody's learned before. Is that true?
That is correct.
Okay. So it's really, actually, this whole unit is very applicable and useful outside of class. It's something that you'll see probably next week. Probably we'll get there by next week. You'll see us using this for money that you can take to the bank, literally, and use that money to predict how much money you could have if you invest in a savings or something. So it's really, really good math. So let's get this kind of boring graphing stuff out of the way, and then we can focus more on that. What's different about this? This is going to be our parent function. It's kind of small, but what's different about it that we've never seen before in this class?
The x is
Yeah, it's the exponent now, okay? Which changes things a lot. That means as x grows, our exponent changes with it. And so now we're taking our base, which in this case is 2, to bigger and bigger powers. So does anybody remember the graph of an exponential function?
It's like, yeah.
Okay, so some of you are getting there.
Or exponentially.
All right, so when you make a table of values, basically you're just doing x and then f of x. And pick values of x. You don't have to do a certain pattern. So I did say start with some negatives. So let's do like negative 10.
Oh, shoot. I started with -3.
Okay. All right, well, let's do negative 3.
I was doing
Negative 3. How about negative 4? Okay. First thing I'm going to remind you, I'm hoping it's a reminder. That means over here, that is 2 to the negative 4, which is what?
160.
Okay. First lesson, I suppose we'll say. First thing, like big idea that I don't want you to forget. Negative exponents have nothing at all to do with the sign of the result. Okay? They don't change the sign of the result in any way. So this is not negative anything. Everybody good on that?
Yeah.
Okay. Do you have a question?
Doesn't it just mean like it's less than 0?
Not necessarily.
Okay. It just is moving the...
It depends where the negative exponent is. So, but you're kind of thinking right. So here's what I want us to think through. Let's do 2 to the 4th, which is what?
6.
Okay, 2 to the 3rd.
8.
4, 2, 1. Okay. Anything to the 0 is 1. That's going to be something that you use a lot in this unit. Okay, now look what's happening. Like each time we do what? You
Yeah.
divide by 2. So, what do you predict our next result should be? 2 to the negative 1 should be divide by 2 again, right? So this should be 1 over 2. And again, we're dividing by 2. So 2 to the negative 2 should be 1 over 2 squared, which is 1/4. So notice all we did was take the negative exponent, move the whole thing to the denominator, and make the exponent positive. Which does make it less than 0, like you said. Everybody good on that?
Yeah.
Okay. What if it's already in the denominator as a negative? Like that.
Just switch.
It goes to the numerator as a positive. So negative exponents trade position of the whole base, meaning top to bottom. They trade position and switch the sign of the exponent, not the sign of the overall answer. Okay? Can we remember that?
Yeah. They changed the.
Change position. So like if you look here, this is in the numerator. Now it's in the denominator with positive exponent. So it's 1/2. If it's already in the denominator as negative, you can rewrite it in the numerator as positive. So it switches place and sign. Okay? Alright. You don't like that? Me neither. I tried to get a new one and it didn't work, so still waiting on that. I do want to leave some room here because the better you understand this behavior of this function before we just memorize the graph, the better off you are. So we know this now is actually let me write it out. It's 1/16, but put the base into the denominator with the positive exponent. So 2 to the negative 4 is 1 over 2 to the 4, which is 1/16. So pretty close to 0, right?
Oh, so that's why.
Huh?
They said that's why it never gets to 0.
Yeah, good job. Okay, so if we did 2 to the, we'll just skip around a little. 2 to the negative 1, again, is 1 over 2 to the 1, which is 1/2. Okay, anything to the 0 is just 1. And then what starts happening as we go the other way?
Well, it's bigger.
Let's skip a little. What's 2 to the 10th? Do it on your calculator. We're just doubling, right?
10,
Times
24.
2, times 2, times 2, times 2.
4,024.
Okay? So think about a typical function, meaning so far we've done linear, quadratic, polynomial, which was like cubic, quartic, and we've done rational, which was really weird looking graphs. Compared to those, these ones have consistent behavior, they're steady, but grow really quickly, right? Like already, if you think about graphing on a typical graph from x and y are both out to 10, negative 10, it's already at 1,000 by the end of that small graph, okay? So by 20, what's 2 to the 20th? Is it double this? No. What's 2 to the 20th?
1, 0, 4,
Wait,
8,
3,
5, 7,
4
6.
digits. 3 digits.
Is that what you said?
6.
Oh, wait. 6.
So that is.
Okay, so just 10 more out, which isn't that far into a graph. We're already over 1 million. So second thing rather that you need to get out of this is that exponential graphs can grow really quickly. Not all of them do, but they can. Or they can shrink really quickly. Okay? So what happens if we went backwards to a big negative, like 2 to the negative 20th? What would it basically be?
Be close to 0.
So
It'd
close
be-
to 0.
That'd be 1.
It's approximately 0, but just above it, right? So what are we creating out to the left? So think about coming further and further left. What are we creating as we go that way? It's a word we used a ton in this unit we just finished. Asymptote, yeah. Will it ever reach 0?
No.
No. Will it ever cross 0?
Yeah.
Nope.
No, because then it'll have to be 0.
Because basically we're taking 1 and dividing it by a bigger and bigger number, but it isn't ever going to be 0. It's effectively 0, but it's not effectively. Okay. So hopefully you're visualizing this graph, and here's the 10, out to 10. So we saw that like out to the 4th, it was barely above 0. Out here, 1 over 2 to the 8th, I mean, it's even worse. Worse is kind of a relative word. Out here, it's huge. What's the y-intercept for this? So,
Is it?
yeah, 2 to the x. So we plug 0 in there, it's just 1. Okay? So again, it has this horizontal asymptote, and then it shoots up from there.
Does that mean the y-intercept will always be 1?
Okay, so he just asked, will the y-intercept always be 1? Well, we can do stuff to this parent graph to move it around, change its shape a little, that kind of thing. And what do you think that will do to the y-intercept?
Make it bigger than change.
It can change it, right? So think about taking this and shifting it left. What would happen to the y-intercept?
It will be a lot
It
higher.
will be.
Right? Now it's higher, the y-intercept is higher. Okay, and same if I take this whole thing and shift it right, maybe it's not launching up until over there. So its y-intercept is almost 0. What else can we do?
Shift it
Down. We could just move the whole thing down here, and now its y-intercept is maybe negative. Okay? Okay, so he's bringing up, what about, can we flip this thing back?
Yes.
What do you think?
I'm pretty sure you'd be able
Yep.
to.
How would we?
Negative 2, negative
Coefficient.
2, negative.
Negative out front, yeah. So see, we're going to see the same thing happening as we have so far, which is A, H, and K change this graph in predictable ways. Okay? Now, one thing that's different about these that we haven't seen is if we take this 2 and make it a number that's smaller than 1, like this, 1/2 to the x, what happens?
And the curve will be, it'll curve
Later.
slower.
It's going to do this, completely different shape. Okay? Sorry, I'm trying to hit it. It's the same idea, but it's decaying, we call that. Okay, and it will approach the asymptote that direction. Okay, so this is a weird thing about this particular parent, is that 2 is not, like all of our other ones, like y equals x, that was the linear parent. We can modify it, but it's still the same structure. X squared, we can add things to it to move it and change its shape, but it's still the same thing. That was true with all these. This one, not so much. Like it has a completely different meaning, and it's totally okay to change the base. And it's still considered an exponential function. So there's that little bit of confusion on this, but you'll pick it up quickly, I think.
So last year, we change the horizontal asymptote from like 0 to like 50%. Can we do that?
Yeah.
Do this?
Yeah, so basically he's bringing up, like, what if we wanted to change this asymptote, you said, to 3, right?
Yeah.
So basically that would involve taking this whole thing and shifting it up. How have we done that in the past?
Adding
Yeah.
to
Okay, so if we do 2 to the x plus 3 out there at the end, that shifts this whole thing up, and now we have a horizontal asymptote here, and it's going to go through 4, like our new y-intercept would be 4, right? Yeah.
What if we did, if we did 2 minus 1 to the x plus 3.
Okay.
2 minus 1 to the x, we get shifted, right?
Like this?
Or no, because that would just be 1 to
Yeah.
I don't know. Or, I know what I'm trying to say, but I don't know how.
Well, which way are you trying to shift it?
To the right.
Okay. So keep in mind, let's see if I can remind you. So for quadratic, we had a x minus h squared plus k. And h was
Oh,
where?
Yeah. It was moving them left and right.
H is where? Like a description.
It's right after this.
Yeah, it's like with x in the function definition, right?
Oh, so we'll.
So where would we have to put it with this to do what Broly wants? 2 to the, yeah, which way would that move it?
Right.
So this whole thing would shift to the right one, okay? Which means now this y-intercept would actually be on 1. That's 2. This graph is scaled weird. Would actually be on 1. And then what would the new y-intercept be? Higher or lower?
Lower.
Yeah, because 2 to the 0 minus 1 is 2 to the negative 1, which is what?
It's
1/2.
1/2. Okay? So this would do that instead. Okay, if we wanted to shift it left, what would this look like?
Plus
Plus 1 or plus whatever we choose. And then, of course, we can start combining all of those and move it up and down and left and right. Okay? What would this do? What if our base was like 4 to the x?
is
Like negative
Moves
exponentially fast.
Yeah,
It basically.
that's a good way to say it. What is this one's y-intercept?
1.
4 to the 0 is still 1, right? And as we go out here to the left, like 4 to the negative 4, or third, let's say, is 1/64th. That's still pretty small. So it's still going to look the same until here, and then it will just shoot up faster.
So it basically vertically compresses.
Stretches.
Yeah, stretches. It horizontally compresses.
Yep, horizontal compression.
So I have a
Okay,
question.
I'm going to do one more, and then let's see if it happens to be yours. What if we stick some constant out front? Like 3.
That was A, and A moved it up and down.
A
No,
stretches.
that was K, moves it up and down.
yeah,
A
stretches
stretches
it.
or
Or-
compresses.
Good job, guys.
Oh, yeah.
Holy cow, you guys are amazing. This is great.
Oh, just keep saying that every
Aw.
day.
I'm serious. Like, I could stand up here for 3 days in some classes and not get this far. So thank you. Good job. I'm not joking. Like, that's for real.
That's really bad.
Yeah.
That's horrible.
All right, Broly, go ahead.
So everything to the negative, like just say to the negative 1 is 0.5. Like if you're multiplying anything by a negative exponent, is it always the same?
No. First of all, let's don't say multiplying by a negative exponent. Just taking it to a negative exponent. But what would this be?
That would be negative 1/4.
Yeah.
Or, I'm sorry,
Yeah.
positive 1/4.
1 over 4. Remember, it just goes to the denominator and changes the exponent sign. So it's 1/4. And then, like, 4 to the negative 2 would be what?
1 over 6. Why don't you say negative? Why would you? Oh.
So it is dependent on your base, for sure.
Well then, how come it's the same? So for the look at the graph.
Okay.
F of x equals 2x and then 4x. How come it's the same on the left?
I mean, it's not exactly. It's just, so you're picking up on a good point. Like, he's asking out here, why am I drawing it looking the same as 2 to the x? And it's not exactly, but it's just not that different.
Okay.
Like, if we plug these into Desmos, which is probably a good idea, you'll see.
Oh, that's cool.
Oh, yeah.
That looks funny.
Oh. What's that happening?
Okay, so
So 2 to the x. How about this? So that, wait a minute. 2 to the x, that's better. And then, do you want to do 4 or something even? Yeah.
Do 10.
Right. We'll make it even a little bit stronger. I keep hitting the wrong button.
Whoa.
2 to 10 to the x.
Oh.
Okay. So do you see how it out here you can't even tell the difference?
So the higher the number,
Even though the
closer
base
gets
is
to
a
the
lot
y.
bigger. Sorry, what?
Okay, like the higher the number, the closer it gets to the y, like the more horizontally it's
The more.
Yeah, because it's once it starts to launch, it's just way more. Yeah.
So to make it like go down, would you do like
Yeah.
negative, let's say 2 to the x?
Okay. So let's take this one, and he's asking how do we make it flip the other way?
Okay.
Yep.
Oh, yeah.
Okay, now here's something that you have to distinguish. That one is decreasing, but it's, well, how would you describe the decrease?
Exponential decay.
It's not.
As
Decay
limit-
is when it goes.
Okay, so do you guys remember the word concavity?
You.
Okay, so this is an interesting thing. Look,
Concaves down.
this one, the y values are decreasing. Okay?
The x values are.
So it is decreasing overall. The function is decreasing. But the concavity is what? Which way is it concave? Concave down. Whereas this one is decreasing, but it is concave up. So, weird, right? Both of those have decreasing y values, but their concavity is totally different.
Okay.
Okay? So, this is, for those of you taking pre-calculus, this is one of the things you'll start talking about pretty early on. And so it's kind of an interesting concept that you can have a function doing a similar thing but different concavity. So this one, I want you to think of, so slope is rate of change, right? Do you agree here the slope, let's do a different color. So slope is pretty close to 0.
Yeah.
And then here it's what? What sign?
Negative.
Negative, but only just a little. And then here,
It's
Negative, but
bigger.
more negative, more negative, really negative, right?
Yeah.
Okay. So the rate of change, are you guys good with the triangle? Rate of change?
Yeah.
Okay. Is decreasing. It's getting more negative, right?
Yes.
And rate is already a rate. Like if I put slope there, it's already, so the rate of change of the rate of change is negative. That's how we say what I just wrote.
That's so confusing.
Yeah. The rate of change of the rate of change is decreasing.
The rate of change.
It's
times
getting more
2.
negative. Okay? What is this one doing? Well, it's super negative here. It's less negative, less negative, less negative,
Basically.
almost 0. So its rate of change is what? Increasing.
Can you do the rate of change times 2 is increasing? So they don't have to go like the rate of change
Oh.
of the rate of change.
Yeah, I wouldn't. Anyway, that's how you can distinguish concavity. Okay? So I want you to take note, because in our unit, this black line is exponential decay. This is not. It's a different thing. Like it's dropping off its value sharply. This is, but in a different way. Yeah.
Just like a throw it out there question.
Sure.
When it's like,
No, ask, okay, can we have like a break? Like you exponentially grow and then you stop and then you grow.
Not just for an exponential function, but you could if you defined a piecewise function, which looks like this. So if I define, and I don't, usually we have time to talk about this at the beginning, but we've kind of taken it out. It's a brace defined function, like we draw it with a brace. And so let's say we did 2 to the x, we'll just use the one we've been looking at. 2 to the x for, where do you want to start? Like 0 at the y-axis? Okay, so for x between 0 and 10. Okay? And then, what do you want it to do after that?
I want it to grow.
Well, this is growing,
I
like
want
that.
it to, I want it to like move over.
Pause,
Yeah.
okay? And then we would say f of x equals 6. No, it's going to have to be bigger than that. Just at 10, let's do that a little shorter, because we are at 1,024. So let's do
5.
4, that's all. What's 2 to the 4th? 16, okay. Okay, and then let's say it's 16 for 4 to 20. I mean, not 20, to 6. Okay, and then what do you want it to do?
And then, can it drop? Can it decay?
Yeah, we could do a whole different thing. We could have it decay, we could have it hump down like a parabola.
Yeah, I want it to actually
You want it to what?
came down.
Okay, so let's do like negative x squared. And then if we wanted it to connect, we'd have to make sure we make that at 6, negative x squared is 30, no, at 6 it would be negative 36, so we'd have to add 36 plus 16 is 52, so we would have to have this be plus 52, and then that would be from 6, anyway, and then we could just have that go forever after that, okay?
Oh, wow.
So that's called a piecewise defined function, and here's how that would look. Here's how that would look. Purple one would look like this. It would start at 1, and it would shoot up. Up to 2 to the 4th, which is 16. Okay, and then the red one, it would pick up from there and go over, just as a flat line, at 16. And then the green one would take off down like that from there. And then these tell you where those functions exist. So like this would be a 4, this would be a 6, and then forever after that. Yeah.
So that means you can't pass the horizontal asymptote.
Well, because this purple, the one that has a horizontal asymptote, is only defined from 0 to 4. So it doesn't have a horizontal asymptote.
Each piece has its own horizontal asymptote?
No. Because this only has, 2 to the x only has a horizontal asymptote back here.
Oh.
And for this function, it's not even defined back there. So, does that make sense?
Yeah.
Oh, yeah.
Because there's no definition. We're saying start at 0. There's nothing before that. Yeah, like this whole thing is f. Does that make sense? Those are cool, huh?
Yeah.
You actually study those a fair bit in calculus, so early on at least. And probably, I guess you probably did in pre-calc too, so you'll see that. But they're called piecewise defined because it's pieces. Want a break? Okay. Guys, thanks for all these questions. It's awesome in our notes.
Oh, it's gonna scratch my eyebrow.
We're like,
No, I
7 more weeks after today.
Yeah.
And once those 18% peak is over, we fly
with this order, that's doable. I could live down there.
Oh my gosh, so one of my friends went to and then we called last night for she came down for her spring break, which was this week. And so we were cleaning up and stuff, and then last night we called her. And just journal, maybe when we talked for the last 30 minutes.
Alright, you guys, a, b to the x, that's how we're going to define this parent function. B is called the base, which we've been looking at as a 2, maybe a half, those different ones we've seen. And of course the big difference is that x is in the exponent now. If b is greater than 1, it's growing. And if b is between 0 and 1, it's decaying. Okay, b cannot be, actually let's do it where we don't have to write as much room. B has to be greater than 0. It can't be 0 or negative. Because if we just did 0 to something, 0 to something, that's kind of pointless. And if it's negative, we're like flip-flopping back and forth, and it doesn't make a function. Okay?
So,
I'm going to translate that into words just because it looks kind of weird with these other two. B must be greater than 0, just to add that in there. Yeah. Okay. When we were looking at the graph, what was the domain of this function? This is no longer a domain of exclusion, so we can just actually write it out like we used to.
It was fun like writing them. X can be everything, but it can never be this.
Yeah, it is kind of fun. So remember, domain is X.
Might be.
Infinite, yep.
Can we?
How about range?
I mean, that depends on the.
Well, for the parent function, but yes, of course it depends, right? Range 4, 2 to the x is 0 to infinity. I mean, we're gonna have different ranges depending on what we do to the function. Good.
Will it have full strings?
No. No more holes.
I'm glad that they don't know. Oh yeah, Alex.
Last unit was the hardest graphing that we do. Just so you know.
Oh, good.
Those
So
the
it's
only
only-
things.
Unless we can get to the trig graphing.
Oh,
that-
that's
that
No,
might be
no,
a little-
So I'm
I
very
think we're good at this one.
Why would you say that?
We have a horizontal asymptote at y equals 0, 4, 2 to the x.
I haven't.
I'd like to get to the trig stuff, but I doubt we will.
Do we have first class terms?
For this? No.
How would that work?
I don't know, that's what I was thinking.
You're like, you can only ever grow to 4.
Okay.
4 days of money, that's it.
In terms of transformations, you guys picked up on that really fast. So this part should be quick.
I don't think that's what I don't know. I don't know. What are we writing now?
You don't necessarily need the parentheses, but I think it helps clarify it a little. So just A, H, and K, just like always. I wonder if we can combine some of this into a couple boxes. A, yeah, let's do it this way. If A is positive, it's normal. If A is negative, it goes the other way. So just call it a reflection. But do put the little picture. And then the usual, if A is bigger than 1, what does it do? It's a stretch. If it's between 0 and 1, it's a compression. Unless, I mean, in other words, it grows faster or slower, like it used to.
What's in blue right there?
Reflect the word?
Did that say
Reflection.
What was
Compression, yeah. Alright. H. If it says X plus H, I don't like that. I don't want to write it that way. That would be confusing. Don't put H there, but if it says X plus a number, then which way does it go?
Up.
Right.
Left.
Oh, left. Right, I'm tweaking.
Yeah, so H is negative, so it goes left. If it says X minus a number, H is positive, so it goes to the right. What color should K be? How about blue? Purple?
Probably should be.
Purple is the best color.
I'd say a dark blue is better, but purple's close up.
You saved yourself there, but.
I like
up there,
that blue
but
that looks purple.
There's
That's
a lot
what I
of
mean.
blues.
Which one?
The really like
Lights purple.
that like looks like purple almost. It's like a really dark blue.
Well, there's midnight blue, and then there's periwinkle, which look like a light blue.
I don't even know what the name of it is. But
So the only
I
time
love
blue
like
is
lilac and
Indigo?
lavender. Those are the
You mean
best.
indigo?
what?
Okay, so
Indigo.
with K, just at the end, we need to add a pretty important note after you get that. If you add the K, it goes up, minus K, it moves down. We've written this lots of times this year, but this one has an additional piece that the horizontal asymptote is Y equals K. So it controls that, where that tail, kind of you could call that like a tail goes.
Mine is much simpler than trying to do like long division or trying to figure out which out of the 3 cases is it. Don't get me wrong.
Yeah.
I love case one.
Let's put in a quick reminder. Base to the 0 is 1. And for the y-intercept, set x equal to 0 and solve.
What was that name? Talking trash? Talking trash.
Sounds serious over there.
Oh. You just jinxed us.
Because this is literally, I mean, you'll do some, but this is literally all we're doing with graphing in this unit.
Good.
We'll do a little bit with graphing log functions, which is kind of they look like this a little bit, but
Isn't log to the 1 0?
Oh, yeah, no,
well, it's, okay. You don't say log to the,
Just log to 1. Yeah.
now this, we're going to learn this, but we have lots of different bases, just like we do for exponentials, we have lots of different bases for logs. If you just look at your calculator and it says log, it's log base 10. So 10 to the 0 is 1, is what this is telling you. But we can have any other base, like log base 2, but that's still the same, because 2 to the 0 is 1. So in this case, it doesn't depend on the base. Alright. Yeah, let's graph that one. Do you want to do it with me, or do you want to do it on your own? Or,
I want to try it. Yeah. Let me go grab some graph paper. You want some of those?
Okay.
Let's grab a nice. Ryan, you already finished?
Man, I didn't have
Why
it.
is that so high?
That's like 2,000. See, that's what
I think it's a
And then you said
Yo, I got the ground.
alright. So on your notes we wrote if B is between 0 and 1, it's decay, but I think we should probably go put what that looks like.
It goes like this.
Okay.
Growth.
Here.
I don't have space. Does that have?
Growth is the normal.
So I just put my hand in the wrong direction.
Yeah.
Oh.
Okay. Growth is this one.
No.
And then decay is not that one flipped over. Alright.
It's going.
No, it's
January
just
that
the other
October
direction.
1st,
Yeah, it comes.
last one day.
Dude, all my friends have broken.
Hey, I'm gonna.
Yeah.
Okay.
Literally, like,
I don't see what.
over 10.
Now think about what's happening every time. Back on this one.
This was in October.
Okay, make sure you're listening because we haven't talked about this yet. When this was 2 to the x, and we did 2 to the 1, 2, 3, etc., what was happening each time?
They were multiplying by
It was doubling, right? So 2 times 2 is 4, times 2 is 8, times 2 is 16, etc. when the base is half, what's it doing each time?
It's not divided by 2.
It's dividing by 2 or halving each time. So now it would be 1/2 to the 1 is 1. 1/2 to the 2 is, I said 1/2 to the 1 is 1. I meant 1/2.
Yes, so 1/4.
1/4, which is a half of a half. Okay. 1/2 cubed is 1/8. So now you see the denominator doubling, which means the overall value is halving. Okay. So if we're dropping by a half each time, not a quantity of a half, but by half of the previous value, that explains why it looks like this, right? Because once we get down here, everybody look here. Hold your pencils just for a second. Like once we get down here, why is it approaching the asymptote?
Because it's having everything, so it's getting smaller.
Yeah, and it's having a small number, right? Like half of a 1,000 is teen, right? It's not much of a change. Whereas up here, like half of 4, you see it drop a lot. Okay? So, what does the 5 do?
It vertically stretches.
It does, yeah. Does it change the y-intercept?
No.
Yeah. Because 1/2 to the 0 is what? I need to put yi for intercept. So 1/2 to the 0 is 1 times 5 is 5. So our y-intercept is 5. And then the shape of this, like you could plug in another couple points like we did a second ago. So 5 times 1/2 to the 1 is 5 times a half, which is 2.5. Okay, 5 times 1/4 is 1.25, which is like there. And that just gives you a little bit of a better clue as to what the graph looks like. You don't need to do very many points, but it's hard to graph with the shadow. Something like that. It's not exactly because I can't see when I do it, but where's our horizontal asymptote for this? At 0, because we didn't shift it up or down at all, right? Okay. So it's hard to tell you on these for the y-intercept. I can't just say, oh hey, it's where h is or where k is, because a, h, k all change where the y-intercept goes. So we need to just check it. Just be careful with that. All right, let's do another one. Well, there's the real one, so that one's the same. How about that one? I'd like to find a better one. A, sure. Try A.
Okay.
So like I was saying, I think it's a good idea to graph the parent function each time first. So in this case, it would be 5 to the x. Remember that we wrote in our notes, and we on that poster up there, the parent is 2 to the x. But because of the way that these work, 5 to the x is, you can treat it as a parent and modify it as well. Okay, there's just a lot of variety in that. So we saw a little bit ago that 5 to the x goes through 1 and something like that. Okay? How does the x plus 3 change this? Okay, so it's x plus a number. We wrote that that means it goes left 3. Here's how you can think of that. This 1, what is our y-intercept for the parent, is now shifting over to being the y-intercept on 3. It's not the y-intercept, but it'll be 1 when the function is shifted over. Okay? So, and then everything else, you just take this and copy it through that point. Okay? What's the actual y-intercept for the blue one, for the modified function? So we do 5 to the 0 plus 3, which is what?
1 to 25.
Yep. So it's big. It's like way off of our graph, right? And that happens a lot on these. Because they grow so fast, you're not always going to even be able to graph it. So it's just going to shoot up, something like that. I'm not looking for perfect graphs, just big ideas. Of course, we can give all the information. This one wasn't a graphing question. Did you guys even read what it said?
Yeah.
It says, how does the asymptote and intercept compare? So we kind of answered that. The asymptote is the same.
It just shifted over.
No, the asymptote is the same.
No, I'm talking about the, like the actual function. It just shifted over.
Oh, yeah. Okay. How'd you do? Okay.
Somewhat okay.
Does the domain change?
No.
Does the range change?
No.
No. Same range, 0 to infinity.
Sounds like my origin story.
Okay. I did ask you about that other one, but then I covered it up. I don't know if I can get it back without changing this whole thing. Let me temporarily do this. What does a negative x do you think?
It flips it.
Oh.
It's going to reflect it over the y-axis.
Oh, yeah.
Okay? So it's going to look like decay now. In fact, the green one is that function. So do you see how it makes it look like decay, even though the base is 5? And then there's our blue. The blue one is the one we just graphed. What else? How would this change? It says describe the graph in terms of transformation. So we need to use words like translation, stretch, compress.
Yeah, there we go.
What's the R word? Reflect.
Look over the.
Okay. That single little mark right there changes our range, doesn't it?
Yes.
What would the range be for this one without graphing it? Can you tell me?
-0 to negative infinity to 0.
Nope.
No.
Negative infinity to 1.
Oh, yeah,
Because it's now going to approach 1 instead. It's going to look like this. Rough.
Almost
Like that's
close.
very rough, right? Very rough. Okay. And I'd like to get to this. Do we have time? How do you feel about this graphing stuff? Are you feeling okay with it?
So, practice on
We're done with graphing for the exponential stuff. That's the end. Okay? Yeah.
That makes me happy.
You miss graphing.
Call me weird.
Probably the only one in here.
Outcast me, I don't care. I'm a fan of rap.
Okay,
I don't like math.
That's all the graphing for exponential stuff. I think it'd be good if we could talk about growth and decay. Are you guys good if we do that?
Yes.
You don't look good.
No.
You want to practice graphing?
Yeah.
And pick this up Monday?
Well, that depends. Never mind.
Yes. I think we're good.
That makes sense. Let's have a cost power.
That's not what I meant.
Did you mean that we're watching
I don't even know where you get magic school books.
Well, that's what-
Oh, I don't have one.
Oh, I did. Well, we could sign in. I could literally, there's like a QR code and I could just sign in with my phone. I do
There's
that
always
every
YouTube.
day. So I probably left it there.
Literally during your class, I just wasn't in magic school.
Seriously?
Yes, because I'm so far ahead of the class that
During what class?
web design.
All right, growth and decay. We're going to write some general equations.
Why did you write it on that and not on the line?
Well, because then I'll write growth, decay. This is like a section title. Do it your way. You don't have to copy mine.
I already copied it.
No.
Please.
Well, you can always make your notes your own. There's a couple guys in here that don't even use the purple thing.
Yesterday, we had to do like, we had to like virtually put out a fire and I clicked the wrong fire hydrant, and this guy was like, "Oh, why'd you do that? Do you even know what oil's made of? What does it come from?" Yeah, dinosaurs. I was like, and he's like, "Why'd you click K? Because that's for kitchen. Are we in a kitchen? What building are we in?" It's like, "Alrighty." And I clicked the wrong one. Let's get over it.
Did you know this?
Sweet.
I would have said
Was this like a simulation on a? Why do you say clicked?
Well, okay, it was like a virtual fire. So we had like an iPad that showed like a fire, but it wasn't really there.
Yeah, I
It was
gotcha.
like a big fire hydrant thing.
Fun.
But he was a real person. He made me really mad. But it's okay.
Because you did the wrong fire.
I clicked the wrong one.
Extinguisher.
He
Yeah.
said it was oil, so I just assumed kitchen oil.
I see.
I would just pressed oil and set it.
Okay, growth. Ready? Ready?
Yeah.
Well, dinosaurs ate plants, so get out of here with that assumption.
Guys, growth again means obviously that this should be shooting up. What we're going to do is give you a template equation for both growth and decay that you can use to write function rules for these real world problems that we encounter. And a lot of the problems we do in this unit are applied, meaning in context. Okay? So you can, let's do g of t, because a lot of times it's growing over time. And of course we'll need to describe what each of these terms mean. So basically you'll start by writing this and then fill it out with what's given in the problem, and then you can use it to solve. Here would be an example. The population of a certain town is 5,000 people. It's growing 2% per year. What will the population be in 5 years? That's how that would sound. So we have a rate given, which was 2%. We have a time given, which was 5. And then we have a starting population, which was what we call A.
You said we could use this money, so could this be like interest?
This would be for simple interest, which isn't common. So we will have specific formulas for compound interest, which is real world. Yeah.
So in a real world example, a starting value isn't the y-intercept.
Yeah. In this one, for this one.
Because usually when I hear starting value, that means y-intercept.
It is in this one too. Yeah. Because look, A is the starting value, like 5,000 people. So if I plug t as 0, this whole thing is just 1. And so it's A. Yeah. All right, let's go define terms. So A is your starting value. R is the rate. But here's a pretty critical part. It needs to be as a decimal, not a percent. In other words, if I say 2%, you can't plug 2 in there. What do you have to put?
0.02.
Good. Holy cow, that's awesome. Ooh, I have to wait sometime. Like, what's 0.75 as a percent?
75.
Were you actually asking?
Yeah, it really was.
I thought you were just like saying that.
Okay, here's the thing about the time. Is that it has to match. I'm not writing anything. Hold on. Has to match the rate units. Okay? Here's what I mean in my example. If I tell you the town is growing 2% per year, but then I say, what will the population be in 6 months? You can't plug 6 in for t. What would you plug in for t? 0.5. So make sure t matches the units of the rate. And then similarly, if I said it's growing at 2% per month, what will the population be in 10 years? What would you put? 2% per month, population in 10 years
12 times
would be 120 would be t, okay? Good. So again, this is a template equation. You'll write this. It's just like if we wrote down the Pythagorean theorem or like a the sine of theta equals opposite over hypotenuse. That's this. You plug in the things you know and solve for the ones you don't. Okay? So then we also have one for decay. And it looks almost identical, but it's 1 minus the rate instead. That way it's less than 1, right? That way it's dropping, not growing. And all the other stuff is the same, so we don't need to write it twice.
This for this one would just be like minus 2.
Yeah. Yeah, so guys, Nate's asking, can we use this idea for money? Like, oh, I just deposited $500 and I'm getting interest. Will I get money? Like, what will be my balance later on? And the answer is yes, but this would be what we call simple interest, and no banks do that. It's all compounding, meaning interest on interest on interest, and it grows faster. I'll show you that. We get actually a whole section on that. So you'll have different formulas because of that. But it's good. I actually had to use it just like a week ago in real life, talking to my bank. And it was cool. It was nice to be able to.
So you can potentially outsmart your bank.
Potentially? Just kidding. No, those guys are smart too, yes, for sure. Here's an example. Population was about 4.6 million in 2010 and grew at a rate of 1.3% for the next 4 years. So write the function and we'll also find out what the population is. So tell me what to write. We're going to start with our template because it says it grew. It grew.
Is 4.6.
Okay.
Well, 1 minus.
Plus.
What? Yeah, plus. See, it says plus. I'm all
Point
on
010.
Oop, I forgot the 0.
3.
Point 0.013 to the 4. Okay. 1.0 or 1.3% for the next 4 years implies that this is annual. It doesn't say it specifically, but it kind of is embedded in it. All right, plug that in, see what the population will be then. Just do 4.6 and just know that you'll say million when you're done.
Power of 4.843 0.04956.
Okay. You got a 9 here?
No, I was agreeing. I said,
Oh.
yeah.
Okay, so that's kind of that's a useful thing. Like, what besides money, what kind of things grow? Okay, plants do, plants, trees,
Bacteria.
your yard, bacteria. What did you say?
Exponential.
Interest, the amount of students on the school.
Potentially, yeah.
You can do,
Lots of things. Yeah.
Like the whole thing.
like how much notes you have to
Because that's
fill
where.
up
My
in
dad.
that container,
Okay.
or to put into a little cap.
Okay.
My dad.
Your dad?
No, my dad.
Oh, your dad. Why? Don't grow your debt.
I'm in the hole right now.
Grow your savings.
Like,
Oh, real quick. Here's a common way of having a question asked. What will the population be in 2040? So do you put 2040 in for T?
No, you.
What would you put?
the amount of
Thirty.
Yeah.
You
So
said 30.
years.
That's a reading thing, but yeah, you guys are good.
30